Good morning. In today's session, we will see about Unit 4, Queuing Theory, and this video is about the introduction session. So, when is a queue formed? A queue or a waiting line or congestion is formed if the service required by the customer can either be a man or a machine, and if the service which is required is not immediately available, then this leads to the formation of a queue. That is, if the current demand for a particular service is going to exceed the capacity to provide the service, then this results in the formation of a queue. The queue's size may either be decreased or it can be entirely prevented by providing additional services. This additional service may result in a drop in the profit when we are considering it from the point of a customer's or provider's side. On the other hand, excessively long queues may result in the loss of sales or it may lose the customers. Hence, the problem is to obtain a maximum balance between the cost which is associated in providing the facilities and also the balance to be achieved without meeting the demands of the loss of the customers. So, queuing theory provides an answer to these problems. There are three main characteristics of a queuing theory. The first one of it is the input or the arrival pattern. The input describes the manner in which a customer arrives and joins the system. It is not possible to observe and control the actual movement of the customers. So we take a period of time, like say 1 minute or 1 second or in 1 hour, how many of them arrive and they join the queue. Or we take the time taken between successive arrival, that is a first person arriving and the next person coming and joining in the queue in the next time. So this is not going to be a constant, as we know that the people can arrive at their own pace and the rate of arrival is going to change from person to person or from place to place. So it cannot be treated as a constant, but it will become a random variable. The mode of arrival of a customer can be made to be assumed to have a probability distribution, and the number of arrivals per unit time or between the inter-arrival time can be modeled to suit the nature. In a queuing theory, we assume that the number of arrivals which happen per unit time follows a Poisson distribution with a mean lambda. Thus, the time between two consecutive arrivals has an exponential distribution with mean 1 by lambda. Also, the input process should specify the number of queues that is going to be permitted to form, the maximum amount of queue length that is allowed, and the maximum number of customers who require the service. That is, the nature from where the sources emanates. That can be either finite value or it can be infinite in value. The second thing which we'll have to know about a queue is the service pattern or the service discipline. That is, the mode of service is represented by the means of the probability distribution of how many customers are being served per unit time, or what is going to be the inter-service time, that is the time taken for service from one customer to the next immediate customer. We consider the number of customers serviced per unit of time has an Poisson distribution with mean mu and inter-service time that has an exponential distribution with mean 1 by mu. Also, the service process specifies the number of servers, the arrangement, whether they are arranged in a parallel way or in a series way, as well as the behavior of the queuing system that depends entirely on it. Only one queue is permitted to form. The last of the thing which we need to know about a queue is the queue discipline. The queue discipline specifies the manner in which the customer forms the queue or the manner in which they are selected for services when already a queue is formed. There are four most commonly used queue disciplines. The first one is the FCFS or FIFO, which can be expanded to first come, first serve, or first in, first out. The next one is the LCFS or LIFO, which serves for last come, first serve, or last in, first out. The third one is the SIRO, which is the selection in random order. And the last one is something based on priority you're selected for the service. Like you may be an elderly people, so you will be given a concession, or you may be an ex-serviceman or a paramilitary force personnel. So in such case, a priority will be given for the selection which is being made. Now, how to represent a Q in form of symbol? This symbolic representation was first given by Kendall, and it is known as Kendall's notation. A queuing model is represented symbolically of the form. Within parentheses, we have A slash B slash C followed by a colon and then a D slash E slash F, where A represents the type of distribution of the number of arrivals that take place per unit time. B represents the type of distribution of the service time. C represents the number of server which is available for providing the service. D represents the capacity of the system, which says whether it is going to be maximum queue length, how many persons that can be accommodated over there in the system. And E stands for the population size from which the queue emanates, whether it is going to be finite or infinite. And last is F, the service discipline that we saw last, like it can be a first come, first serve, last come, first serve, selection in random order, or a priority base. Our syllabus is going to cover two models. The first one, MM1 infinity FIFO and MM1 in KFIFO. Over here, M represents the Markov, indicating that the number of arrivals in time t and the number of completed services in time t follow a Poisson process, which is a continuous time Markov chain. The next M represents the service quantity. 1 stands for the number of server. Infinity represents the capacity of the system, so it can hold infinite number of people, or K in such case is going to be the finite capacity of the system. And FIFO is going to be the queue discipline, the discipline in which your service is going to be provided for. The MM1 model with infinity as the capacity, system capacity, and FIFO as the queue discipline has the following formulae. The probability of n customer in the system, Pn, is represented by lambda by mu whole power n into P naught. The probability of having no customer in the system is denoted by P naught, 0 standing for no customer, which is given by 1 minus lambda by mu. Average number of customer in the system represented as LS, length of the system, given by lambda by mu minus lambda. Average number of customer in the queue given by LQ, representing length of the queue, which is lambda square into mu minus lambda, which can be shortened and written as lambda by mu times of LS, which is the length of the system. Average number of customers in the non-empty queue will be represented as LW, which is given by mu minus lambda. Probability that number of customers in the system is going to exceed the value k is given by probability of n greater than k, which is lambda by mu whole power k plus 1. The PDF of the waiting time in the system is given by f of w, which is mu minus lambda e power minus of mu minus lambda times of w. The average waiting time of a customer in the system, ws, is given by 1 by mu minus lambda. WS, waiting time in the system. Probability that the waiting time of a customer in the system S exceeds T is going to be WS greater than T, given by e power minus mu minus lambda times T. PDF of a waiting time in the queue, WQ, is given by G of W is equal to lambda by mu times of mu minus lambda, e power minus of mu minus lambda times of W, when the waiting time W is going to be greater than 0. And if it is equal to 0, this reduces to 1 minus lambda by mu. The average waiting time of a customer in the system is going to be WQ, which is lambda by mu into mu minus lambda, or WQ, which is represented as lambda by mu into WS. The average waiting time in the queue, if he has to wait from time to time, or the queue is getting formed from time to time, is the conditional expectation of WQ provided the queue exists and WQ is greater than 0 is given by 1 by mu minus lambda. There are a set of formulas called as Little's formula, which gives the relationship between the four of the quantities which we determine, namely LS, LQ, WS, and WQ. The length of the system, length of the queue, waiting time in the system, and waiting time in the queue. The relationship that connects them is given as follows. So, if any of the above quantities are known, and the other three can be found out by using the relation which has been given by the Little's formula. The Little's formula holds good for the queuing model with infinite capacity, but a slight modification for the model with finite capacity has to be made to make these formulas work.